In this video, we're going to be talking about the structure of the nucleus, essentially what different types of particles are found there, and some things we need to know about them. So the nucleus of an atom is found at the center of that atom, surrounded by electrons, but for now we're just focusing on the nucleus. The nucleus contains two different types of subatomic particles, known as protons and neutrons. So protons are particles that have a positive 1 charge. They have a mass of approximately 1 atomic mass unit, and the number of protons in the nucleus is what gives an element its identity. This is known as its atomic number. And it's probably the most important property of an atom because it makes the atom what it is. A carbon atom is only a carbon atom if it has 6 protons. It gives the element its identity. The other type of particle that we have in the nucleus is the neutron, which has a neutral charge or 0 charge. Also has a mass of approximately 1 atomic mass unit. And the number of protons plus the number of neutrons gives us what we consider to be the atomic mass. Electrons have a negligible weight. It's not technically nothing, but it is really, really close to nothing. So essentially all of our mass is coming from the protons and neutrons. So if we add up the number of each, we get the total mass of that atom. Not all atoms of a given element have the same number of neutrons. So all atoms of a particular element have the same number of protons. All carbon atoms have 6 protons. But they can vary in number of neutrons, and we call these different variations on an element isotopes. So we're going to be talking a lot about different isotopes in this unit. So isotopes have the same atomic number, meaning that they're the same element. But different atomic mass. So if we have the same number of protons, that difference in atomic mass must be due to a different number of neutrons present in the nucleus. So the reason why it's important to, or one reason anyways, why it's important to recognize different isotopes is that different isotopes can have different properties in nuclear chemistry applications particularly. They can undergo different types of nuclear reactions. We'll talk more about this a few lessons down the road. But for now, recognize that that's the reason why we care that isotopes exist. So a good example of this is carbon-12 versus carbon-13. So these are both isotopes that exist for carbon. So note that the number that I'm specifying here is the mass, and I totally wrote carbon-12 twice, which was not my intent. And both of these isotopes are stable. But another isotope of carbon, carbon-14 will undergo a reaction known as beta decay. More on that coming soon. To form nitrogen-14. So we have different chemical properties, different chemical reactions that happen for different isotopes. Carbon-12 and carbon-13 don't really engage in nuclear chemistry at all. They're stable as they are. But carbon-14 is not so stable, so it does undergo a nuclear reaction over time to actually turn into nitrogen. So the last thing I want to talk about in this video is nuclear symbols. So the way we sort of represent different isotopes of different elements. So I've already kind of shown how we represent different isotopes in text, just the name of the element followed by its mass. So carbon-12 is carbon-12. Red as carbon-12 means an isotope of carbon that has a mass of 12. We can represent this as a symbol as well. As you know from the periodic table, elements have symbols of 1 or 2 letters, and we can use those symbols to convey information about which particular isotope we're talking about. So the general format for nuclear symbols has the element symbol, and I color code this, has the element symbol from the periodic table, with a couple of numbers. And both of those numbers will be to the left of the element symbol. We have a superscript and a subscript. So the superscript is going to be the mass of the isotope. And then the subscript is the atomic number of the element, or we'll see where this comes into play in the next video. Sometimes it is the charge on the particle. The atomic number is the same thing as the charge on the nucleus. The nucleus contains protons and neutrons. Only the protons have a charge, and they're each +1. So if your atomic number is 6, that means you have 6 positive 1 charges, and your total charge would also be 6. So the charge way of thinking about it is sort of more inclusive, because we can actually use this symbol format for things besides atoms, for things besides nuclei, which we'll see in the next video. So it's usually atomic number most of the time, but if what we're looking at isn't an element, then you kind of need to think in terms of the charge. So I want to take a couple minutes to do a few examples. So let's try to write the nuclear symbols for carbon-14, thorium-234, and europium-152. So why don't you grab a periodic table and pause the video here for a minute or two. Try to write the element symbols, so using this format, for these 3 examples. So for these examples, we'll need to find the symbols from the periodic table as well as the atomic numbers for each of these different elements. So for carbon-14, we find that carbon is element number 6, and it has the symbol capital C. So the mass of our isotope is given to us right here as part of the name, and that is the superscript. The subscript is our atomic number, which is 6, which we get off the periodic table. So then for thorium, that is element number 90, way down at the bottom of the periodic table. It has the chemical symbol capital T, lowercase h. When you have a 2-letter symbol, it's always the first one is capitalized and the second one is lowercase. If it's just a 1-letter symbol, it is always capitalized. So the mass we were given for this particular isotope is 234, and then the atomic number, which we found on the periodic table, is 90. So that is the symbol for thorium-234. Note that the mass is always the mass for that particular isotope that we're talking about. So when we're writing these symbols, we're specifying the particular isotope of interest. We're not copying the mass off the periodic table. The mass given on the periodic table is an average of all of the different isotopes. So we want to be specifying in these symbols one particular isotope that we're actually talking about, not taking the mass off the periodic table, which is an average of all of the isotopes that actually exist. So last but not least, we have europium-152. Europium is element number 63, also down near the bottom. It has the chemical symbol EU. The isotope that we are interested in is the one with a mass of 152, and atomic number, promptly forgot, was 63. So we can kind of fit any isotope into this formula as long as we remember sort of what the parts and pieces are. And I think that's all for this video.